Hey everybody, Mr. Field here, and today we're going to be chatting about the perpendicular bisector. All right, so hopefully you have this in your notes, and let's get started. So perpendicular bisector, the definition itself is any sort of segment, ray, or line that is both perpendicular to a segment, and it's perpendicular at the midpoint of that segment. So if we look at this diagram to the right, and we check out segment AB. Clearly, that's a finite segment. It does not go on forever, which would make this point smack dab in the middle, point P, the midpoint. And I know that's the midpoint because of these congruency marks telling me that the distance from A to P is the same as B to P. So in this case, it looks like AB is the segment that's being cut or being bisected by line CP in this case. So the definition, again, is any segment, line, or ray that cuts a segment, another segment, in half at its midpoint, but it's also perpendicular, which is why you see that right angle symbol. And remember, the perpendicular symbol is like an upside down capital T. So that's a perpendicular bisector. Now there's actually a couple of theorems that we can actually use that once we know there's a perpendicular bisector involved, that is, we can actually use this information to help us set up and solve problems. So one of the most important ones starts, well, right here. So we know points that are along or on the perpendicular bisector of a segment are always going to be equidistant from that segment's endpoints, which kind of might be confusing. Let me show you in the picture and make it make more sense. Hopefully you would agree that point C here is on the perpendicular bisector CP. That means that the distance from A to C is the same distance from C to B, or B to C, however you want to say it. So that's the perpendicular bisector theorem. And this happens for several reasons. We haven't talked about it just yet, but in our next unit, we're going to talk about congruency. So this is actually when we talk about it, since both of these triangles share this side in between, we know we can add congruence marks there. They already have, and we already know that these two sides are the same. So this is going to be the side angle side congruency postulate, meaning I know that triangle CAP is exactly the same size and same shape as CBP. So that's the SAS, side angle side, get sassy, congruency postulate. But again, we're going to talk about that in the next unit, so I don't want to spoil too much. We'll talk about how that is and why that works. But I know that these two triangles are the same, which means that if these triangles are exactly the same size and same shape, that means that they're hypotenuse. Yeah, hypotenuse of each of these triangles. Notice, again, if this is a right angle on the right, the one on the left is going to be a right angle, and the C value in A squared plus B squared equals C squared Pythagorean theorem, or the hypotenuse in a right triangle, right? Each of these would be a hypotenuse, meaning hypoteni combined. They would have to be the same length because everything else is the same. So we're going to talk about that in the next section. But long story short, perpendicular bisector theorem tells you that if there's a point, like point C, that's on the perpendicular bisector, we know it's going to be equidistant from the endpoints of the segment that it's cutting in half. All right, so let's move on to a couple of example problems of how we can actually use this in the coordinate plane. As you can see, there's several steps. So when you're finding a perpendicular bisector, the first thing you're going to do is, well, before this, you're probably going to be given 2 points. You're going to plot those points. Once you plot those points, you're going to find the midpoint, the halfway point first, well, using the midpoint formula, which is this. We add the x's from the two coordinates, cut it in half, comma, we add the y's and cut it in half, and that finds you the midpoint. And then you're going to plot that point. And once you have that midpoint, then you find the slope of that given segment. You can either do rise over run, or of course you can y2 minus y1 over x2 minus x1. Keep in mind, one of my favorite sayings in this section is, should we trust the graph or should we trust the math? We should always trust the math. Why? Because the graph could have human error. So the formula is probably the most accurate way to go. But most of you probably could use the graph and figure this out as well. And then we're going to find the perpendicular slope. And if you remember, just for an example, let's say the slope of my line happens to be 1/2. The perpendicular slope to that would have to be the opposite reciprocal. So it would have to be negative, because notice this is a positive 1/2. So the opposite of opposite reciprocal means one's positive, one's negative. And then, of course, reciprocal essentially is the flip of the fraction. 1/2 becomes 2/1. And, of course, negative to make it opposite. So we know the line, the perpendicular bisector, is going to have a slope of negative 2/1 in this instance, and it's going to have to cut through the midpoint. So again, all we need is 2 points to graph a line. So once you have the slope, and once you have the midpoint, you can start at the midpoint and simply do rise over run to plot the rest of your points using the slope. All right, so let's try a quick example and go from there. Let me just switch over to my blank slate here, and let's get started. So let's talk about this first one. As you can see, I'm going to do the first one. You're going to do the second one. So, well, let's check it out. So we have points D and E. Let's plot those points. So I'm thinking 5, -1 means right 5, down 1. So it looks like D is hanging out here. And then, of course, point E, -11. Ooh, they're being sneaky here. They're going off the graph, up 1, 2, 3. So it's not exactly the easiest. So keep in mind, from here we could then draw our best version of a line, which obviously I didn't do a very straight job. So again, trust the graph, trust the math. Well, obviously I'm not good at drawing straight lines, so I'd probably trust the math. I mean, the midpoint's probably somewhere up in there. So maybe it's like 2, 1. I don't know though, because my graph's not that good. So we're going to trust the math here. We're going to take these 2 points and plug them into the midpoint formula and get our answer. So I like to stay organized. You know, first X, first Y I see, second X, second Y I see, just to stay organized, because, you know, in general, every point, every coordinate has an X and a Y value. When you have more than one, it's nice to stay organized. And we're just going to plug that right into this formula, x1 plus x2 divided by 2, comma, y1 plus y2 divided by 2. So I'm thinking we're going to add the x's. So we're going to have 5 plus -11 divided by 2, comma, and then we're going to have -1 plus 3 divided by 2. So from there, we have to simplify. -11 plus 5 should get us -6 over 2, comma, -1 plus 3 should get us 2 over 2. So I think it's actually at -3, comma, 1 is where our midpoint should be hanging out. So -3, 1, 2, 3, up 1. I was close. I said -2, 1. So I was a little bit off. So I guess my graph isn't the worst. Definitely not the prettiest, I can tell you that. And I'm just going to finish this off and act like it's going on forever. By the way, I put some arrows on the end to confirm that. So we have the midpoint. That's check mark number 1. We also have to find the slope of the line that we currently have, because once we have that, we can flip it and change it to the opposite sign, and then we have the slope of the line that's going to be going through our midpoint and cutting this segment in half. So let's do that. Let's get a different color though. I'm getting tired of this. Let's go purple. Why not? It's a purple kind of day. All right, so let's find the slope. Again, we want to pick really nice points, and obviously they gave us 2 of them right off the bat, and my line's not that nice. I mean, maybe we could graph this on Desmos or another program like that and get a better graph, and then do rise over run. So I don't know if I really want to trust the graph. I mean, it looks like you go down 1, 2, then over 1, 2, 3, 4, 5, 6, 7. So it looks like -2, 7. Let's see if that continues. Down 1, 2, right? 1, 2, 3, 4, 5, 6, 7, 8. Ooh. So I don't know. I mean, I'm not really happy with using the graph. So let's trust the math. Let's do the same 2 points, right? We're going to use the same x1, y1, x2, y2, and let's use the actual slope formula. Y2 minus y1 over x2 minus x1. Again, if my graph was better, I'd probably trust it, but it's really not. So I'm going to go ahead and trust the math here. So we're going to do y2 minus y1, and you got to be careful with these double negatives here. Y2 minus y1 would give us 3 minus -1. So we're going to have a double negative going on, which I always like to use, or a double, another set of parentheses, right, just to make sure I realize it's double negative. So we have 3 minus -1, or -11 minus 5. So double negative becomes plus positive, so we get 4 over, I think, -16, which if we reduce that, kind of run out of room here, should get us 4 goes into 4 1 time, 4 goes into 16 4 times. So we have a slope of -1/4, which is clearly different than the -2 over 7 that I got. So again, trust the math, not the graph when you're doing these problems. Easy to make a mistake when you draw by hand, is my point. So now that we know that the slope of this line is -1/4, we can find the slope that's perpendicular to that. And I know the slope that's perpendicular to that is going to be, maybe it's not the best color, the opposite reciprocal, meaning I'm going to flip it to 4/1. And notice our original slope of this pink line is decreasing, which makes sense based on our graph. This one should be increasing. Looks like up 4, right 1, up 4, right 1. And that's when we're basically home free. We know the perpendicular bisector to this pink highlighted segment has to be, well, perpendicular. It's going to meet at a right angle, and it has to cut it in half at the point in the middle, that green midpoint. So we can start at that midpoint and go up 1, 2, 3, 4, right 1. Up 1, 2, 3, 4, right 1. Of course, the more points, the merrier. The more points you include, the easier it is to actually see the line and be more accurate. So I'm going to do the opposite and go down 1, 2, 3, 4, left 1. Down 1, 2, 3, 4, left 1. So our perpendicular bisector, gosh, I'm off today, everybody. Sorry. Still a little better. All right. So that blue line represents the perpendicular bisector, and it should be meeting at a right angle. So the first thing you have to be able to do is be able to construct these perpendicular bisectors. So after that model, right, if you could please try the you-do, right, maybe pause this video, try the problem on the right, see if you can graph the initial line, find the midpoint, find the slope, opposite reciprocal of that bad boy, to get the opposite reciprocal slope, or the slope of the perpendicular line, and then graph the perpendicular bisector. Once you do that, we'll talk about the last thing. All right, folks, welcome back. Hopefully the you-do problem was not that hard. You hopefully found the perpendicular bisector and graphed it. The last thing I just want to briefly talk about is perpendicular bisectors within a triangle. We can use the skill that we just learned, right, to find the perpendicular bisectors, and I'm saying that plural for a reason, of all three sides of this triangle, the green side, the blue side, and the red side. If you were to construct, meaning find the midpoint, which I'm going to estimate just for these purposes, of course we wouldn't really do this in real life, I'm going to estimate that looks like it's the approximately where the perpendicular bisector would go. It would probably look something like that for that green line. And then if we find the halfway point of this line, then maybe a perpendicular bisector looks something like that. And of course, again, did a terrible job. My apologies, folks. Let's try that again. So maybe it's somewhere around here, so to speak. And then we have it doing something like this. Then, of course, we can find the perpendicular bisector of this line by first finding the midpoint and then drawing a line that's perpendicular to it. And, of course, they're going to have some sort of meeting point when you draw all three. That's called a point of concurrency, right? Or these would be called concurrent lines. And I don't want to spoil too much of the fun, but when you find a point of concurrency, it actually has some implications for some real world problems, which we're going to actually try in just a few minutes. So thanks for watching the video on perpendicular bisectors. Hope this was helpful. Catch you next time.